and then from 4 to infinity. So a little college algebra review here. Interval notation. Just to jog y'all's memory a little bit. So if you're talking about a solid interval that includes its endpoints, that's when you use the square brackets. And if you're talking about an open interval, so an open interval includes everything between A and B, but not the endpoints. That's when you use the parentheses or the round brackets. Yes, sir? Yeah, there is an open bracket. Right here? Because we're not continuous right there. Oh. Actually, we do need to be a little bit careful there, Dante. You have a good point. Yeah. And actually, I do this every time, and I forget about it. So there is a little bit of a difference between what I was taught and what Pearson says for these. And I'm glad that you asked, because this is always an issue when my students go into the homework. So in Pearson, and I don't agree with this, which is my own issue, but in Pearson, they will actually consider this function to be continuous from -4 to 1 with a little hard bracket there because it's filled in. I don't agree with that because the left-hand limit doesn't equal the right-hand limit there, so that shouldn't be continuous. But I always teach that, and then my students go into Pearson and they get the wrong answers. Yes, sir?
So if you have like a defined line, so say like x equals 1,
Mm-hmm.
I mean x plus 1, that's the function.
Mm-hmm.
And you have defined points like -2 all the way to like +1.
Mm-hmm.
Like that's just like, I mean, that's the intervals, that's how long the line is.
Oh, so like a line segment like this?
Yes.
Okay.
Would there be a general limit at those endpoints or no?
No, and that's where Pearson, they kind of, and again, I don't like it, but we'll talk about it. So Pearson, like for a line segment like that, how I was always taught continuity is like, let's say that this is over here at like 2, and this is at -2. How I was taught continuity, it would say, okay, this is continuous from -2 to 2, and it's not continuous at the endpoints because we don't have a general limit at the endpoints. So that's one school of thought, I guess. What Pearson is saying is that, hey, since you do have a filled-in point there, what Pearson does is it calls it like right and left continuous. Because what it says is, okay, since that left-hand limit doesn't exist, like if we're over here, yeah, I can't talk about the left-hand limit because I don't have any points over here. What Pearson says is, okay, you actually are continuous at those values since you have a point on the graph that you can relate to, and since the limit that's available to you does go to that point. So you kind of have to combat, well, again, if I just teach it like that, it wouldn't be an issue, but so be a little bit cautious with the filled-in endpoints in Pearson. If you get an answer wrong on those, more likely than not, it's just a difference of a bracket. I think it makes a lot more sense to do the soft brackets, but they didn't really ask me what I thought, so I guess this is what we've got to go with. So in our graph, or where our function is continuous, We will have a closed bracket with that -4 because that is filled in there. Now everywhere else, so like from the left here, it makes a lot more sense to leave that -4 off because we don't actually have a point right there. But then right here, definitely makes sense to leave off that point since we don't have it. And at 4, we're not even defined there. So we definitely wouldn't want anything there. All right, let's. What's that? With the closed bracket there. Because that's what Pearson seems to like. There we go. All right, so some more continuity, discontinuity. So these graphs should look pretty familiar. We looked at these graphs pretty early on to talk about limits. So at 1 and -1, bless you, we've got some asymptotes here. And asymptotes cause a problem for us because at 1 and at -1, both of those are undefined. And if you're not even defined at a point, then you definitely can't be continuous at that point. So this one's a little bit more cut and dry. Our function would be continuous just everywhere except those two values. So we'd go from -∞ to -1, -1 to 1, and then from 1 to infinity. So any other thoughts on the brain at this point about this particular example? Okay. Not too bad so far. Very, very similar. So where would this graph be discontinuous? 1 and 3, yeah. Making my life easy. So yeah, 1 and at 3. We've got some vertical asymptotes there, which definitely fall into the discontinuous category. So everywhere from -∞ over to 1, and then from 1 to 3, there you go, and then 3 to infinity. All right, y'all are coming along nicely. So now we don't have the nice viewpoint of a picture. So these are a little bit more difficult. But remember, you're never going to be asked in this class to kind of like reestablish that a wheel is round or anything like that. Mostly what you're doing when you're talking about whether a function is continuous or not is you're thinking, okay, where does this function have any issues? And something that's very, very close to the process that we use to determine if a function is continuous is the same process that you used in college algebra to talk about the domain of a function. Because if you think about it, what do you look out for with a domain? You look for any undefined points, zero divisors, asymptotes, all that stuff. We're doing the same thing here. So for our first one, f of x that's up there, f of x is a polynomial. It's got positive powers of x. So it's got an x squared, an x to the 7th, a regular x. And polynomials are something that's been given to you as continuous. So if you identify something as a polynomial, and you have in your head that polynomial functions are continuous, I don't need you to reestablish for this question, well, this is continuous because all polynomials are continuous. Here's a proof of why all polynomials are continuous. That's a little bit too much. All I really need here is that f of x is a polynomial. And all that means is that it is continuous everywhere. Now for the one below it, g of x, kind of similar here. G of x is a rational function. And if you remember our rational functions, they're largely okay, except at their vertical asymptotes. So the only thing that we have to watch out for g of x is we've just really got to look out and make sure that if we have any vertical asymptotes, that we leave them off. So from your college algebra days, if you wanted to find a vertical asymptote, all you do is you take your denominator and figure out when it equals 0. And that's where you have your vertical asymptotes. So moving that 2 over to the other side, and then dividing by 4, you get that x equals, there you go. So that means that that rational function, except for negative 1/2, it has values everywhere. You can plug in any other value other than negative 1/2 and get a value out on the other side. So this means that g of x would be continuous from negative infinity to negative 1/2, yep. And then from negative 1/2 to positive infinity. Just because we've got positive powers of x. Okay. So if you have numbers, x's, x squareds, x cubes, x to the 7th, any combination of those is going to be one of our polynomials. Yeah. All right, now logarithms, similar deal. Logarithms are nice continuous functions where they're defined. So this question is kind of asking what the domain of a logarithm is. And if you remember from logarithms, and it's okay if you don't, to figure out where a logarithm is defined, you're just taking what's inside of the logarithm. And with a logarithm, you can't plug in negative numbers or 0. Now, a logarithm can be 0 or negative, but you just can't plug in a negative value into a logarithm. So you just have to set up a little inequality here. So you know that you need x minus 4 to be greater than 0. So you just move the 4 over to the other side. So logarithms are pretty well defined, and they are continuous wherever they're defined. So that means that h of x would be continuous from 4 to infinity. All right, we saved the best one for last, tangent of x. So if you had Kinsey for pre-calc, hopefully you've got this one, and I imagine Sosina went through it too. But where are the asymptotes for tangent of x?